Have you ever accidentally tapped a wooden spoon against a stainless steel pot?
Oh, yeah, all the time.
Right. And you immediately hear that really sharp, high-pitched clink sound.
Yeah, this very distinct noise.
It is. And then, maybe just a few seconds later, you reach out and you touch the handle of that exact same pot. And assuming it hasn't been on the stove yet, it feels just freezing cold against your bare skin.
Right, it has that icy bite to it.
Exactly. And it is something you experience, every single day, completely intuitively. I mean, you do it without ever really stopping to question the underlying mechanics of it at all.
We really just accept it as a basic fact of life, don't we?
Totally. We just know metal clinks and feels cold, and wood thuds and feels basically room temperature.
Yeah, that's just how the world works to us.
Right. We treat our hearing and our sense of touch as these two completely, totally separate streams of information about the world.
And, that separation makes perfect biological sense. I mean, we have years to process acoustic information, right? And then we have a nervous system with these really specialized thermoreceptors in our skin, and those process temperature.
Which are totally different biological systems.
Exactly. Because the hardware in our bodies is separated, we just assume the physical phenomena out there in the world must be separated too.
Like they have nothing to do with each other.
Right. We categorize sound as an acoustic wave traveling through the air. And we categorize heat as some kind of thermal energy or invisible fluid contained inside an object.
But the reality is actually far more unified than that. The pitch of that sound you hear when you strike the metal and the sudden chill you feel on your skin when you touch it, they are not random disconnected traits.
I don't.
They are actually the exact same microscopic phenomenon. It's just being translated differently by your body. And that is our mission today.
It's a really exciting one.
It really is. We are exploring this fascinating area of solid-state physics to uncover a beautifully unified law, one that connects what we hear sound, with what we actually feel, which is heat.
And the underlying text we are working from today really breaks down this physics of sound and heat. It looks at how everything around us is dictated by these invisible, microscopic forces connecting atoms.
Which sounds super abstract, I know.
It does, but the goal today is to take those cold, inorganic formulas that physicists rely on in the lab and translate them into the actual voice and warmth of the everyday objects you interact with.
Okay, let's unpack this. Because to understand why a pot clinks or why it feels cold, we really have to completely redefine what sound actually is when it's moving through a solid object.
Right, we have to kind of throw out our everyday intuition.
Exactly. Most of us just imagine sound as invisible ripples moving through the air, right? Sort of like waves on a pond.
Yeah, that's the classic analogy.
But solid-state physics requires us to look at it as a purely physical, mechanical process. Sound is essentially a microscopic telephone.
I love that analogy. And to understand this telephone game, we need to accurately visualize the structure of a solid material first.
Okay, so paint that picture for us.
Imagine that stainless steel pot. If we zoom in far enough, we don't just see a continuous solid block of matter.
Like a smooth gray wall.
Right, it's not that at all. We actually see a massive three-dimensional grid of individual atoms.
Just trillions of them.
Exactly. And these atoms are not just floating randomly near each other. They are locked into a highly specific arrangement. They're held together by chemical bonds.
And the source text points out that physicists often conceptualize these bonds as microscopic springs.
Yes, and that is a highly useful way to visualize it. An atomic bond isn't this rigid, unbreakable rod. It's more of a delicate balance of electromagnetic forces.
So it has some give to it.
It does. The positively charged nuclei of two adjacent atoms are naturally trying to repel each other, but the negatively charged electrons are pulling them together.
So they're stuck in this sort of tug of war.
Exactly. They settle into an equilibrium, which is just a comfortable resting distance. If you try to push the atoms closer together, the repulsive forces push back.
And if you pull them apart?
The attractive forces pull them back in. So they behave exactly like physical springs.
So when I take that spoon and I strike that metal pot, I'm not just making a noise in the air, I'm delivering a massive dose of kinetic energy right to the atoms on the surface.
You are physically hitting them.
Right, which forces them out of that comfortable resting position we just talked about. They physically get shoved forward.
And because that first layer of atoms is connected to the second layer by those microscopic springs, the second layer gets pushed too.
The spring compresses.
Exactly. It compresses, it builds up potential energy, and it violently shoves the next atom in line.
And then that second atom shoves the third.
And the third shoves the fourth. This mechanical chain reaction of physical displacement traveling through the atomic grid, that is literally what sound actually is inside a solid object.
That's so wild to think about. The signal being passed down the line is simply physical movement.
Just atoms bumping into each other.
Right. And this introduces a really critical concept in materials science, which is elasticity, or basically the stiffness of those atomic connections.
Physicists measure this stiffness using a metric called Young's modulus.
Which sounds incredibly intuitive.
It does, but you really don't need to dive into the deep mathematics of stress and strain to grasp the concept here. Young's modulus is fundamentally just a measurement of how much force it takes to stretch or compress those microscopic springs.
And how violently they snap back into place once you do.
Exactly.
So if a material has a high Young's modulus, its atomic springs are incredibly stiff and unyielding. The electromagnetic bonds are immensely strong.
Right, and if it has a low Young's modulus, those springs are weak, forgiving, and, well, kind of floppy.
Let's consider how the stiffness of those connections alters the speed of our atomic telephone game, because this is where it gets really visual.
Yeah, let's play this out.
So think about a line of people, and they're trying to pass a physical signal from one end of a football field to the other.
Okay, I'm picturing it.
In the first scenario, every person in the line is holding onto a highly rigid, solid titanium pole. So person A holds one end, person B holds the other.
And then person B holds another pole connecting to person C.
Exactly, all the way down the entire field. But in the second scenario, the people are connected by entirely different lengths.
What are they holding?
They are holding super long, highly elastic, really floppy rubber bands.
Ah, okay. The mechanics of how the signal travels in those two scenarios are going to be completely different.
Night and day.
If the first person in the titanium pole line decides to aggressively shove their pole forward, the result is basically instantaneous.
Because the pole is rigid.
Right. Because the pole is highly rigid, which represents an extreme Young's modulus in our analogy, it doesn't absorb the energy, it transfers it immediately.
So the microsecond person A pushes.
Person B is violently shoved backward.
The signal doesn't get bottlenecked at all. Person B moves, the next pole moves, person C moves. The wave of physical displacement travels down that entire line of people almost instantly.
The speed of the wave is incredibly fast.
Now contrast that with the line connected by the floppy rubber bands. When person A shoves their end of the rubber band forward, the band simply goes slack.
Or if they pull it, it just stretches.
Right, it stretches and absorbs all that kinetic energy, converting it into tension, until finally it builds up enough force to sluggishly pull person B forward.
So there is a massive mechanical lag there.
Huge lag. By the time person B actually registers the pull and starts to move, person A has already finished their movement completely.
And then person B slowly pulls the next rubber band,
which slowly stretches and eventually pulls person C. The entire chain reaction is slow, it's delayed, and it absorbs a ton of energy along the way.
And that dynamic right there is the fundamental mechanism determining the speed of sound in any material.
Stiffness of the springs.
Exactly. If the microscopic springs are weak and floppy, meaning a low Young's modulus, the vibration travels slowly. The atoms essentially have to wait for the weak spring to compress enough to push the next atom.
But if the springs are stiff...
If they're incredibly stiff, a high Young's modulus, the moment one atom twitches, the stiff spring instantly forces the neighbor to move. The wave of displacement propagates at blistering speeds.
So, simply put, sound travels faster through materials with stiffer bonds.
Yes, that's the core rule.
But the physics of how researchers actually calculate this velocity relies on a balance of two competing forces. We need to look at how that stiffness interacts with mass.
Right, the mathematical relationship defining the speed of sound is really elegant. The velocity of the sound wave is driven by the stiffness of the material divided by its density.
And the formula from the text, we usually see this written as velocity equals the square root of Young's modulus over density.
That's the one. Let's focus on the conceptual relationship there, though. The stiffness, the strength of the springs, is driving the velocity up.
The stiffer the spring, the faster the signal.
Exactly. But density is on the bottom of that equation. It's acting as the denominator. It's the counterweight.
So it's actively trying to slow the velocity down.
It is. Density basically represents the physical mass of the atoms packed into a given line. This brings Newton's laws of motion into play, specifically inertia.
Because heavier objects require more force to accelerate.
Right. An atom with a massive heavy nucleus is simply harder to push than a light atom.
So if person B in our telephone line suddenly weighed like 1,000 pounds, it would be much harder for person A to shove them, even if they were using that stiff titanium pole.
Exactly. The inertia of that heavy person would naturally slow down the entire wave of movement.
The speed of sound is basically the final result of this tug of war. The stiffness of the springs trying to whip the vibration forward, fighting against the heavy inertia of the atoms trying to resist the movement.
And we can see how this tug of war plays out by looking at a few baseline materials. Let's start with the air we're breathing right now.
Okay, air. Air is a gas, so the structure is entirely different from a solid metal pot.
Very different. In a gas, the molecules are not locked into a rigid three-dimensional grid at all. They are highly dispersed, floating relatively freely, and really only occasionally colliding.
So the intermolecular forces, the springs, are incredibly weak compared to a solid.
It is the ultimate floppy rubber band scenario, combined with just a whole lot of empty space.
Because there is virtually no stiffness connecting the air molecules, a physical displacement takes a relatively long time to propagate. Right?
Exactly. One molecule gets pushed,
Yeah.
and it literally has to physically travel through empty space until it collides with another molecule.
Which then has to travel to hit the next one.
Right. And this results in a speed of sound of about 340 meters per second.
Which is pretty fast in human terms, but on a physics level, it's why we experience things like the classic thunderstorm delay.
Oh, that's a perfect example.
When lightning strikes, it superheats the air and creates this massive shock wave of displaced molecules. But because the connections between the air molecules are so weak,
That mechanical wave takes several seconds to travel from the storm cloud all the way down to your ear.
you see the light instantly because light travels differently, but you have to sit there and wait for the sluggish physical wave of sound to finally arrive.
Exactly. Now let's contrast the air with a solid block of iron. Iron is a metal, meaning its atoms are locked into a crystalline lattice.
And iron is highly dense, right? The
Yeah.
atomic mass of iron is significant, and those atoms are packed really tightly together.
Very tight, very heavy.
Now, wait a minute. This is where I have to push back a little, because this is where the tug of war gets confusing for me.
Okay, let's hear it.
If iron is incredibly dense, its atoms have a lot of mass. They have high inertia. And according to the relationship we just discussed, with density on the bottom of that equation, shouldn't that heavy mass act as a massive brake on the system?
That's a really logical conclusion.
Right, like shouldn't a higher density slow the sound down significantly? Why does the stiffness of the spring overpower the heavy weight of the iron atoms?
It's a great question. It does act as a brake. Density is trying to slow it down.
Yeah.
But the opposing force in iron is metallic bonding.
Okay, what does that mean in this context?
In a metal lattice, the atoms share this sort of sea of freely moving electrons. And those electrons lock the positively charged nuclei into an intensely rigid structure.
So the springs are strong.
The Young's modulus of iron is absolutely massive. The strength of the springs completely overpowers the weight of the atoms
Overpowers it. By how much?
by an astronomical margin. The sheer overwhelming stiffness of those metallic bonds vastly outweighs the dampening effect of the heavy iron atoms.
Wow.
To return to our analogy, it is like having that 1,000-pound person in the line, right? But instead of pushing them with a titanium pole, you're launching them forward with an industrial hydraulic ram.
Oh, wow. Okay, so the driving force is so absolute, the heavy mass is forced to move almost instantly anyway?
Exactly. Because the springs are so unimaginably stiff, the speed of sound in iron accelerates to roughly 5,000 meters per second.
5,000 meters per second? That's almost 15 times faster than it travels through the air.
It's incredible. The stiff springs just whip that atomic vibration through the lattice at incredible speeds. The density is fighting back, but the stiffness wins the tug of war decisively.
Okay, so stiff materials transmit sound lightning fast. The physical wave just tears through the rigid structure.
Exactly.
But I want to pivot here because we've been focusing on sound. If we connect this to the bigger picture, what happens if we stop hitting the material with a hammer to make a sound, and instead we put it over a fire?
Yes. This is where we shift our perspective from acoustics to thermodynamics. And it really requires a fundamental paradigm shift for most people.
How so?
Because down at the level of the atomic lattice, sound and heat are the exact same physical mechanism.
See, that is such a difficult concept to internalize because our bodies process them so differently, you know?
Absolutely.
We don't listen to a fire to know it's hot, and we certainly don't try to feel the acoustic vibrations of a conversation to understand what someone is saying.
Right. Our macro-level human biology has evolved highly specialized sensory organs to detect different amplitudes and frequencies of energy. It's for our own survival.
Right, evolutionary biology.
But the universe doesn't care about our biological categorization. In the microscopic grid of a solid material, both sound and heat are simply mechanical waves of atomic displacement propagating through the lattice.
Okay, let's trace the mechanics of heat to see how closely it mirrors the telephone game of sound we just talked about.
Let's do it.
Imagine you place a frying pan on a gas stove. You turn the dial, and a blue flame erupts, and it physically engulfs the bottom of the metal pan. What is that flame actually doing to the metal?
Well, a flame is basically a mass of rapidly moving, highly energetic gas molecules.
Okay.
When those hot gas molecules collide with the metal atoms at the bottom of the pan, they transfer their kinetic energy. The metal atoms essentially scream, "ouch!" and absorb this energy, and they begin to violently oscillate.
They shake back and forth around their resting positions within that grid.
Exactly. They can't fly away because they are locked into the grid by those stiff metallic bonds, so they just thrash in place.
And because they're thrashing, they're constantly compressing and stretching the microscopic springs, connecting them to the next layer of atoms.
Right. That violent oscillation yanks on the springs, which forces the second layer of atoms to start vibrating.
And the second layer pulls on the third pulls on the fourth.
It is the exact same chain reaction. The only difference between striking the pan with a spoon and putting it over a fire is the nature of the input source.
Right. A spoon delivers a single macroscopic directional shove.
Whereas a fire delivers billions of chaotic microscopic shoves. But the resulting mechanism, a wave of displacement traveling along the atomic springs, is totally identical.
So heat transfer is this mechanical wave. That's mind-blowing.
It really is. And physicists who are mapping this behavior realized pretty quickly that trying to mathematically track the chaotic, interconnected thrashing of trillions of individual atoms was computationally impossible.
I can imagine. Just too much data.
Way too much. They needed a conceptual shortcut to model how this vibrational energy moved from the bottom of the pan all the way up to the handle. So they created the concept of the phonon.
The phonon. Okay, let's establish what that is. Because the phonon isn't a physical particle you can isolate in a vacuum, right? Like an electron or a neutron.
No, not at all. It is what we call a quasi-particle. It's a quantized mode of vibrations occurring in a rigid crystal lattice.
Okay, break that down for us.
Think of an ocean wave. The wave moves across the surface of the water for miles, carrying energy. But the individual water molecules aren't moving miles, right?
Right, they're just bobbing up and down in a localized circle.
Exactly. The wave is a propagation of energy through a medium. A phonon is simply how physicists treat that wave of energy as a discrete, measurable thing.
They bundle the complex mechanics of the thrashing atoms into a neat mathematical package.
Exactly. And then they track how fast that package travels through the material.
Looking at solid materials through the lens of the phonon makes the distinction between sound and heat incredibly clean.
It really clarifies things.
So sound is a highly ordered phonon wave, usually at a lower frequency, generated by a human striking something, or some macroscopic mechanical force.
Right. You hit a pot, you send an organized wave of phonons through the lattice, and the air carries that specific frequency to your eardrum.
But heat is a chaotic, high-frequency phonon wave generated by thermal kinetic energy. The fire excites the atoms, sending a massive, disorganized swarm of phonons rushing through the material.
But the vehicle carrying the energy is identical in both cases. The phonons are traveling along the exact same atomic springs, governed by the exact same laws of stiffness and density.
Okay, if heat is just phonon waves traveling on atomic springs, then the stiffness of those springs must govern how efficiently a material conducts heat, right? Just like it governs how fast it conducts sound.
Exactly. We calculate a material's ability to transfer heat using a metric called thermal conductivity.
Okay, and there's a formula for that in the text too. Let's break that down carefully for everyone.
Right. When researchers measure thermal conductivity, they're essentially calculating three distinct variables multiplying together. We represent this as kappa is proportional to C times V times L.
Okay, so let's define those.
First, they look at how much energy it takes to get the atoms vibrating in the first place. That's C, the specific heat capacity.
Okay, makes sense.
Then they look at how far the phonon can travel before it crashes into an obstacle, like an impurity in the metal. That's L, the mean free path.
Got it.
And critically, they look at the velocity at which the phonon travels. That's V.
Wait, the velocity of the phonon? But we just established that a phonon is the mechanical wave of displacement.
We did.
And the velocity of a mechanical wave in a solid is the speed of sound.
Yes.
So the V in the heat equation, is that the exact same V we were just talking about?
It absolutely is. The speed of sound is literally a multiplier right there in the equation for thermal conductivity.
That is the ultimate aha moment right there, the common denominator. The speed at which heat transfers through a material is fundamentally mathematically locked to the speed of sound in that exact same material.
They're completely linked.
If the atomic springs are stiff, the speed of sound is massively high. And because the speed of sound is a direct multiplier for heat transfer, a material with a high speed of sound is automatically, inevitably, an incredibly efficient conductor of heat.
They are inseparable properties, born from the exact same microscopic architecture. Fast sound guarantees fast heat transfer.
Okay, now that we understand the theoretical math that faster sound equals faster heat, I think we need to take this phonon concept out of the lab. Let's test this unified law against the materials we actually interact with every day.
I think that's a great idea.
If stiff springs equal fast sound and fast heat, how does that actually translate into the sensory experiences of hearing a pitch and feeling a temperature?
Well, we can start by looking at metals, since they are the most common conductive materials in our daily lives. Take iron or copper, for example.
Right, and we know from earlier that metals are defined by their dense, crystalline lattice and the intense stiffness of their metallic bonds.
They have a massive Young's modulus.
So when you strike a metal surface, those rigid springs force the physical displacement wave to pass from atom to atom almost instantaneously.
Right, the mechanical lag is virtually non-existent. The speed of sound is incredibly high, often several thousand meters per second.
And to our auditory biology, our ears, a mechanical wave traveling at that velocity with a high frequency hits our eardrum and is interpreted as a sharp, high-pitched sound.
Right. The bright, piercing clink of a metal pot is literally the acoustic signature of highly rigid atomic springs.
Okay, so the acoustic signature perfectly confirms the architecture of the lattice. Now let's examine the thermal side, the tactile proof.
Because the speed of sound is so massive, the thermal conductivity must also be massive.
The phonons, the heat vibrations, are riding those exact same rigid springs. They rush through the metal lattice at breakneck speed.
And this dictates exactly what happens when you place your warm, bare hand on a room temperature block of metal.
Let's walk through that.
Okay, so the human body maintains an internal temperature around 98.6 degrees Fahrenheit, while the metal might be sitting at, say, 70 degrees.
Room temperature.
Right. And thermal energy always flows from hotter to colder.
So the moment my skin touches the metal, the kinetic energy from my vibrating skin molecules begins to transfer to the metal atoms on the surface.
Exactly. And because the metal possesses incredibly stiff springs and massive thermal conductivity, the heat doesn't just slowly warm up the surface layer.
It doesn't just sit there.
No. The metal lattice acts as a high-speed thermal vacuum. It grabs the kinetic energy from your hand and shovels it deep into the metal away from your skin almost instantly.
And this is key because the thermoreceptors in my skin don't actually measure the absolute temperature of the object I'm touching, do they?
No, they don't. They measure the rate at which heat is leaving your own body.
That is such a critical distinction. The metal itself isn't generating a chilling effect. Not at all.
It is simply an incredibly efficient thief of your body's thermal energy. The rapid, relentless drain of heat triggers your thermoreceptors to send a massive panic signal to your brain.
And your brain translates that massive loss of heat as a sensation of freezing cold.
So the sharp clink sound and the icy cold feeling of the metal are not two different phenomena at all.
I know.
They are two sensory translations of the exact same physical reality. An incredibly rigid atomic lattice shuttling mechanical waves at extreme velocities.
You are experiencing the identical microscopic architecture through two totally distinct biological interfaces. It's beautiful.
It really is. The unified law holds perfectly for metals. But to really test it, we need to look at materials on the exact opposite end of the structural spectrum.
Okay, like what?
Consider a really common biological material like wood. Whether it's oak, pine, or maple, wood is fundamentally different from a forged metal crystal.
Oh, completely. It wasn't formed by superheating elements into a perfect lattice. It was grown by a living organism. Right. Wood is a complex, chaotic biological composite. It is primarily made of cellulose fibers bound together by a natural polymer called lignin.
And more importantly for our physics discussion, because it functioned as the circulatory system for a living tree, it is heavily porous.
Right. It's full of microscopic tubes.
Tubes, cellular chambers, air gaps, and varying degrees of moisture. It's very messy structurally.
From a solid-state physics perspective, it sounds like a structural disaster.
It is. The springs connecting the molecules in wood are constantly interrupted by voids and water molecules. The intermolecular forces are weak and wildly inconsistent.
So the Young's modulus is incredibly low.
Exactly. Because the springs are floppy and disorganized, wood is terrible at propagating a mechanical wave.
When you strike a wooden table, the kinetic energy tries to travel through the material, but it immediately hits weak, lagging connection.
Right, energy gets absorbed, distorted, and delayed. The speed of sound through wood is drastically lower than in metal.
The wave is slow and sluggish. And when that low-frequency, low-velocity wave finally reaches the air and travels to our ears, we don't hear a bright clink.
No, you hear a muted, low-pitched, dull thud.
The thud is the direct acoustic translation of a chaotic, weakly bonded microscopic structure.
And following our unified rule, if the speed of sound is low, the thermal conductivity must also be severely compromised. The heat phonons simply cannot gain momentum.
Because we mentioned earlier that thermal conductivity relies on the mean free path, right? The distance a phonon can travel before it crashes into an obstacle.
Yes, and wood is essentially nothing but obstacle.
Right. Every time a heat phonon tries to travel down a cellulose fiber, it hits an air pocket or a droplet of moisture or a grain boundary.
And the phonon scatters. It gets reflected or absorbed. It cannot establish a clear, fast route through the material.
So the combination of floppy springs and a chaotic, obstacle-filled structure makes wood a fantastic thermal insulator. It resists the flow of heat entirely.
Which perfectly dictates your tactile experience. When you place your warm hand on a room temperature wooden table, the wood simply does not have the microscopic infrastructure to rapidly shuttle the heat away from your skin.
The thermal transfer is incredibly slow and highly localized.
Exactly. Because the wood isn't stealing your body heat rapidly, your thermoreceptors aren't triggered to send a sudden temperature drop signal to your brain.
So the table just feels neutral or maybe slightly warm because my body heat stays trapped right at the surface where my hand is touching it.
Yep. The dull thud of the acoustic wave and the neutral, insulating feel of the thermal wave are, again, perfect reflections of the same chaotic, microscopic architecture.
Okay, so the structural state of the material dictates everything, but this introduces a really interesting engineering question that I want to pose to you.
Okay, I'm ready.
Wood is inherently a terrible conductor of sound and heat because of its biological, chaotic structure. But what if we could somehow force those atomic springs in the wood to tighten up? Could we trick a piece of wood into acting like a metal?
That is a brilliant question. And it isn't just theoretical. Humans have actually been performing this exact structural manipulation for centuries.
Wait, really? How?
Through a process called pyrolysis. The clearest example from the source material is the creation of a highly specialized Japanese product called binchotan, or white charcoal.
Okay, binchotan. Talk me through that. Binchotan starts its life as standard wood, right? Usually a very dense species of oak.
Yes, ule oak, usually.
Yeah.
And at this stage, it possesses all the acoustic and thermal properties of wood we just discussed. Low speed of sound, low thermal conductivity, dull thud, neutral temperature.
But then the artisans subject this oak to a really intense thermal transformation.
Highly controlled, yes. They place the wood into a specialized kiln and slowly raise the temperature, eventually baking it at temperatures exceeding 1,000 degrees Celsius.
Wow, 1,000 degrees.
Right, while strictly limiting the amount of oxygen, so the wood doesn't simply catch fire and turn to ash.
So what happens to the microscopic architecture of the wood when it's baking at 1,000 degrees in a low oxygen environment?
It undergoes a violent chemical decomposition. At those temperatures, all the free moisture locked inside the cellular tubes reaches a boiling point and completely evaporates away.
Okay, water's gone.
Then the complex organic polymers, the lignin and cellulose, begin to break down. The volatile organic compounds, the saps, the resins, all of it is entirely incinerated and driven out of the wood as gas.
So you are systematically destroying everything that made the springs floppy and chaotic in the first place.
You are burning away all the obstacles.
What is left behind then?
Basically a carbon skeleton. But because of the extreme heat, those remaining carbon atoms don't just sit there loosely. They are subjected to enough energy that they actively restructure themselves.
Like they rebond.
Exactly. They begin to bond together, forming a tight, continuous, three-dimensional network of amorphous and crystalline carbon.
So the chaotic, porous biological structure collapses and fuses into a rigid carbon lattice. The wood has literally been engineered into a brand new material.
The physical upgrade to the Young's modulus is exponential. The weak biological links have been entirely replaced by intensely strong carbon-carbon bonds.
The microscopic springs are suddenly incredibly stiff.
Extremely stiff.
So let's test the new material against the unified law. If we strike a piece of fully transformed Vincha-tan charcoal, the structural reality suggests we should not hear the dull thud of oak wood anymore.
Not at all.
The tight springs should force the mechanical wave to travel extremely fast.
And the auditory result is astonishing. Have you ever heard it?
I don't think I have.
If you take two pieces of high-grade Vincha-tan and strike them together, they ring. They actually produce a bright, high-pitched, almost glass-like metallic chink.
No way, from charcoal!
Yes, the speed of sound through the material has skyrocketed because the atomic lattice has been fundamentally tightened.
That's amazing. The acoustic signature confirms that the carbon springs are essentially acting like metal, which means the thermal conductivity must have experienced a massive upgrade as well.
Oh, absolutely. The obstacles are gone and the springs are incredibly stiff. The heat phonons now have a highly rigid, smooth highway to travel down.
So Vincha-tan possesses a remarkably high thermal conductivity compared to the wood it used to be.
It behaves as a highly efficient heat sink. The transformation is so complete that the tight carbon lattice even allows for the efficient flow of free electrons.
Meaning what?
Meaning you can literally use a piece of this baked wood to conduct electricity and light up a light bulb.
Wait, really? Wood that can light a bulb?
Yeah, it is a stunning real-world demonstration of how tightening the microscopic connections completely alters the macroscopic physical properties of the material.
That is incredible. Okay, so Vincha-tan shows us how far we can push carbon by baking it in a kiln at 1,000 degrees. But if baking carbon creates such a dramatic shift, what happens if we look at the most extreme version of carbon in the universe?
Oh yes, now we're getting to the ultimate boss.
Exactly. To find the absolute physical limit of the unified law, the highest possible speed of sound, and the greatest thermal conductivity, we have to look at how carbon behaves when it is subjected to the most extreme geological forces on the planet.
We have to look at diamond. Diamond represents the absolute apex of the stiffness-velocity-heat relationship.
It is the ultimate structural extreme, and diamond is composed of the exact same element as the Vincha-tan charcoal, right? Just pure carbon.
Right, but the architectural arrangement of those carbon atoms is what elevates it to an entirely different realm of physics.
Because diamonds are not forged in kilns. They are formed hundreds of miles deep within the Earth's mantle, subjected to millions of pounds of crushing pressure and thousands of degrees of heat over billions of years.
That unimaginably violent environment forces the carbon atoms into a state of absolute structural perfection.
How so?
Well, each carbon atom forms 4 strong covalent bonds with 4 neighboring carbon atoms. They arrange themselves into a rigid, 3-dimensional tetrahedral lattice.
Covalent bonding is really key here, isn't it?
It is. Unlike the electron sea in metals that we talked about earlier, where electrons float freely between nuclei, covalent bonds involve atoms very tightly sharing pairs of electrons. They are locked into a highly specific directional geometry.
And that tetrahedral geometry is naturally incredibly stable. The carbon-carbon covalent bond is exceptionally short and strong.
The result is a lattice that fiercely resists any mechanical deformation. Diamond is famously the hardest natural substance on Earth. It simply does not yield.
Translating that into our mechanical terminology, diamond possesses the stiffest microscopic springs known in the natural world.
By far. The Young's modulus is astronomically high. It dwarfs even the strongest titanium alloys.
And because the density of carbon is relatively low compared to heavy metals like iron or lead, that tug of war between stiffness and density is overwhelmingly won by the stiffness.
Totally dominated by it. The springs are essentially infinitely strong, and the mass they are pushing is relatively light.
So we plug those parameters into the physics governing the atomic telephone game. When kinetic energy is introduced into a diamond lattice, the physical displacement wave is forced from one carbon atom to the next, with virtually zero mechanical lag.
The stiffness is so absolute that the speed of sound inside a diamond accelerates to roughly 18,000 meters per second.
18,000 meters per second. Let's just contextualize that velocity for a second. Sand travels through the air at 340 meters per second.
Right.
It travels through incredibly dense iron at 5,000 meters per second. But in a diamond, the mechanical wave is traveling at 18,000 meters per second.
It's hard to even fathom.
That is more than 3.5 times faster than iron. It is an alien velocity. It's pushing the very boundaries of physical mechanics.
And because that velocity is the direct multiplier for heat transfer, as we learned,
The thermal conductivity of diamond must scale accordingly.
The heat phonons are basically riding a flawless, infinitely stiff atomic highway.
The phonon express strain. There are no impurities to scatter the wave, and the springs transmit the energy instantly.
The result is staggering. The thermal conductivity of diamond is about 5 times greater than that of copper.
And copper is the gold standard for thermal management in electronics and high-end cookware, specifically because its metallic bonds conduct heat so beautifully.
But diamond, which is an electrically insulated crystal, outperforms it by a factor of 5 solely because of its extreme acoustic velocity.
It's incredible. And to bring this abstract physics back to the human sensory experience, consider what this massive thermal conductivity actually feels like.
Yeah, here's where it gets really interesting.
Imagine you have a large natural diamond sitting on a table in a perfectly comfortable 72-degree room.
Okay, I'm picturing it. It is sat there all day, so it is completely equalized with the ambient temperature. It's 72 degrees.
Right. Now, if you pick up that diamond and press it gently against your lips.
Which are packed with highly sensitive thermoreceptors.
Exactly. The diamond does not feel like it is 72 degrees.
What does it feel like?
It will feel shockingly, painfully cold. It will feel like a piece of ice.
Really? Just sitting in a room.
Yes. The moment your warm lips make contact with the diamond, that perfect tetrahedral lattice goes to work. The intense stiffness of the carbon springs immediately grabs the kinetic thermal energy from your skin.
And the heat phonons jump onto the diamond's lattice and are violently sucked away from the surface at 18,000 meters per second.
The thermal vacuum is so powerful, so relentlessly efficient, that the local temperature of your skin actually plummets instantly.
And so my thermoreceptors are overwhelmed by the sheer speed of the heat loss. They scream to my brain that I'm touching something freezing cold, even though the object itself was resting in a warm room.
Exactly. The icy chill of the diamond is the direct tactile proof of an 18,000 meter per second acoustic wave. The unified law is perfectly demonstrated.
High pitch, fast sound, and aggressive thermal transfer are inseparable traits born from a single microscopic reality. It's just brilliant.
It really fundamentally changes how you perceive the physical world around you, doesn't it?
Totally. We spend so much time looking at the macro level, the shape of a pot, the color of a table, the sparkle of a gem. But the true nature of how we interact with these objects is entirely dictated by forces we cannot even see.
Yeah.
The stiffness of an invisible spring determines whether a material rings like a bell or thuds like dirt, whether it burns your hand or feels perfectly safe to touch.
You know, solid-state physics often feels deeply inaccessible to most people
Oh, for sure.
because it relies on complex mathematical models, quantized particles, and all these Greek variables describing stress tensors and mean-free paths. It can feel utterly disconnected from the human experience.
But the exact opposite is true. Those equations are the literal blueprints of our sensory lives. The math translates directly into the feeling of a cold handle, the sound of a dropped spoon, the warmth of a wooden floor.
The physics is simply a formal language used to describe the intimate mechanical interactions we have with the universe every single day.
I love that. And we want to challenge you to interact with your environment differently after listening to us. Walk around your house today and run your own physical tests.
Yes, become a physicist in your kitchen.
Exactly. Tap on a stainless steel appliance, listen to the sharp pitch, and feel the cold surface. Then tap on a wooden door frame, listen to the muted thud, and feel the neutral temperature.
And as you hear those sounds and feel those temperatures, try to actually visualize the microscopic architecture.
Picture the rigid, dense grid of metal springs aggressively shuttling vibrations, and contrast it with the chaotic, porous, biological tangle of the wood absorbing and scattering the energy. You are physically interacting with the atomic structure of the universe.
It highlights just how deeply integrated our biology is with the fundamental laws of mechanics. We have essentially spent this time proving that our ears, when they process a high-pitched acoustic wave, and our skin, when it processes a sudden rapid drop in thermal energy, are detecting the exact same phenomenon.
For the mechanical waves of atomic displacement.
Two completely distinct biological senses, interpreting the exact same physical truth.
Which is just so cool to think about.
It is, and this raises an important question regarding how we experience reality as a whole.
What's that?
If acoustic pitch and thermal sensation are merely two sides of the same mechanical coin, translated differently by our nervous system, What other ways that we experience the world might just be different translations of the exact same physical law?
Oh, wow.
What other entirely distinct human senses are fundamentally connected, just waiting for us to zoom in far enough to see the invisible springs linking them together?
That is a completely new way to look at how we experience reality, something to definitely ponder. Thank you for joining us on this deep dive into the hidden, microscopic architecture of our everyday world. Keep questioning the things you touch and hear, and we will catch you next time.